Yeah, thanks. Today I'm going to be talking about some work which isn't done. Usually when you go to conferences, you want to talk about stuff which is maybe not sort of published, but is at least sort of done. This is very much not done because the focus is going to be more on the methods, right? And I think mine is a really nice occasion to sort of afford that sort of thing. So the only sort of thing that we've actually finished within this is sort of the review paper talking about some of the methods and how they could be used. And I think this is going to be sort of the concrete or some concrete examples of how we're actually starting to do the things that we said might be possible. And also sketching out a little bit more of where I think this thing can go in the future. And this is going to also be sort of illustrating sort of one of the new directions in the lab since I came up here at Dartmouth versus some of my earlier work. I did a lot of, as sort of Luke was alluding to, a lot of sort of very controlled, sort of condition-rich RSA types of designs when I was earlier in my career, and gradually sort of during my postdoc and increasingly here, I've been working more and more sort of naturalistic things and actual interactions. And so this is going to showcase a few of the things that we're getting into in that vein. Hopefully it'll be kind of short and sweet and be a little bit exciting for what's going to come next. And I'm going to be focusing on nonverbal behavior. So I think this is actually really nicely sort of complementary talk to Stefan's, because I'm going to be basically talking about everything that he wasn't in this sort of trait impression formation space, the first part of this talk. And more generally, thinking about all the ways that when we're interacting, we're not just interacting by sort of the words and the literal meanings of those words that we're communicating, but using all these other modalities as well, right? We have our facial expressions that can communicate a lot of information. We have sort of body pose and gestural sorts of ways of communicating with other people that are often really important and either sort of deliberately communicate information, like in the case of pointing, where I want to direct your attention, or maybe sort of leakage of sort of information, which I might not want to get out, like nervous sort of thing. But in either case are something that other people can pick up on and use to sort of guide their interactions. And then also in sort of the vocal modality, beyond, again, the sort of literal text of the words that we're saying, there's all this additional nuance that gets added by, the tone of voice or prosody that I'm using, the nonverbal utterances, like, et cetera, that I'm using, right? And also, again, sort of things about my identity, like my accent, for example. So all these things are really important for social interactions, and they haven't been, I think, as much of a part of a lot of the ways that we study these things. So if we really want to understand interaction, I think that the basic premise is here, we need to study sort of all of its modalities. And one of the reasons I think this hasn't been quite as popular in the past is because it's just really hard to do. At least using sort of traditional approaches, right? So if you, for example, collected a video recording with audio of an actual interaction in, past decades, basically, the only way to quantify that, to turn that into numbers that are susceptible to sort of meaningful analysis at a social level, would be to go in and sort of manually annotate it. So either you or your research assistants or some MTurkers go and like look at these stimuli, and maybe they make ratings or like draw like where the skeleton of a person's body is on the slide or something like that. But this is just incredibly intensive, right? So like, maybe you can have somebody go through and annotate, a few hundred facial expressions, but if you wanted, say, every frame of a video to have some kind of annotation, or if you want people to annotate things that people aren't very good at annotating, like how they can draw like a three-dimensional skeleton within an image, then that's actually not going to work really well. It's not going to scale up to the sort of large sample sizes and diverse populations we want to study if we want to sort of capture the full picture of what interactions can look like. And I think one of the most exciting things that's happened in this space in the last 10 years is the sort of rise of deep learning methods that can automate a lot of this, not necessarily perfectly yet, not at human levels yet necessarily, but a heck of a lot faster and more cheaply in most cases than what people can do. And so this allows the sort of research to scale up in really exciting ways and allows us to answer questions which, not for principled reasons, but for sort of purely practical reasons, were kind of out of reach, I think, to past generations of interaction science. So in today's talk, I'm going to look at sort of three cases of these sorts of things. First, I'm going to focus on traits, just like Stefan's talk, but in particular looking at impression updating, not on just the first impression based on static face images. So once you have already seen somebody's face and like, okay, that looks like sort of trustworthy or electable or whatever, then you see them behave in some way, and it's like, oh, actually, maybe not, So how does that process happen? And particularly what role do nonverbals play in making those updating steps? Then I'm going to look at some data that the Talia's lab, Emma Templeton, collected in particular, looking at just totally naturalistic, unconstrained conversations between strangers, and looking at body language in this context, which I think kind of shockingly has almost no like large data sets where people have looked at this. There's a few data sets have been released now, but a lot of those have things like their zoom, and so you can't really actually see most of the body on those ones. You see the head pose or a few sort of insertions of fingers into the space, but generally you can't see the rest of their bodies. Or you have like really constrained and kind of like odd social interactions between people. So things where it's like, oh, we're gonna like mutually mirror each other, and it's like that's interesting, like that's kind of cool, but like I don't really do that with people very often. I don't know, maybe I'm weird, but yeah, that seems odd. Or like with strictly regimented turn taking, sometimes that's necessary in things like fMRI if you want to like separate those things out. But that's again sort of pretty artificial, and it can create sort of or induce odd correlational patterns in the data that might not exist in more constrained situations. And then finally, I'm going to sort of sketch out where the lab is going with using some of these tools in sort of more like real time and trying to actually manipulate, psychological processes in interactions using sort of the medium of the interaction itself. So using nonverbal modalities, for example, or verbal modalities for that matter, as a way to convey psychological manipulation so we can get a causal understanding of these things. So I'm going to start by, as I said, talking about trait impression formation. And this is really sort of the paradigm for that in the last like 15 years, basically, right? Is you show somebody a computer generated face. Generally, it wasn't sort of the nice sort of realistic looking ones. It was sort of a, earlier generation. And I did a lot of these studies. Like I was at Princeton as an undergrad and I participated in a lot of Alex's studies on this. It was nice pocket money as a college student. And I couldn't escape the impression that, with all these sort of like bald and like not particularly sort of stereotypically feminine looking faces, I was looking at like boot camp recruits or like prisoners or something, so it does create kind of like an odd sort of context in and of itself to have these non-naturalistic ones. So I think that sort of movement towards the more naturalistic ones is great. But often you just get a sort of like one piece of like very simple diagnostic information as sort of the thing you're supposed to update on, right? It's like, oh, there's some, bad thing or good thing that this person did. So I write how trustworthy they were just on the face. And then after I get this piece of diagnostic information, how does it change my opinion, right? And of course, we've learned some really useful stuff from doing this, but I think there's a lot missing from this picture relative to how we update our impressions in real life, right? If you think about a situation where like, maybe you swipe right on a dating app based on somebody's face and then you meet them and then you change your opinion about them, like a lot of things go into that changed opinion that are probably not like them telling you I took candy from a baby, right? So some of the things that I think are missing is like a lack of like context and time scale here. We don't know how, when the timing of particular things happens, and also the timing of your own sort of impression updates sort of occurs in relation to those events. We don't have a lot of like actual really nuanced detail, right? So if I wanted to encapsulate that sort of episode of taking candy from a baby, and I wanted to actually convey all of the detail you might get from observing it, I'd probably have to write like paragraphs and not like one really short phrase. And of course, there's a lack of sort of any of the nonverbal signals that we'd get in real life if we were observing this sort of event taking place. So my recently former postdoc Tujin Lin, who's now starting a professorship at University of California, San Diego, has been doing work with me looking at this using the SEND data set. So this is the Stanford Emotional Narratives data set collected by Desmond Ong in Jamil Zaki's lab. And I'll show you what a few of these videos look like in a second. But basically, these consist of, for our purposes, 112 videos that are sort of shareable, that people gave permission to be used more widely, in which a single participant shown against a Black background tells a short emotional story from their own life. So you tell a story of when you got your first job, or when you were dumped for the first time, or something like that, right? And these are pretty short videos. They're 1 to 3 or 1 to 4 minutes on average, or around the range of like 2 minutes, basically. And they've already been transcribed and annotated in a bunch of ways. We tried to improve on a few of these annotations, but these annotations are going to be kind of the substance of what we use as sort of our predictors in this case. It's like things like, all the parameters that you might get out of pi feet if you ran that on a data set, or, taking text transcriptions, in this case done by humans, but then running through a large language model to get some application of the meaning of what they say. So here's just like what one of these looks like.
Yeah, I guess as a kid, like my sister was like the one who took care of me a lot because like we come from a single parent household, and she definitely like stepped up and like was half like a mom to me, half big sister, just like perfect like caretaker. Yeah, I guess as a kid.
Can you hear that well enough? It's going through my laptop, but okay, great. So yeah, that's an example of one of these videos, which I think is pretty representative. You can see, single person on a Black background, talking about some, moment in their life that had emotional valence. We chose a subset of these based on some initial studies where we just had sort of pre-post rating. So we got like an initial rating of a bunch of traits. Then people watched the video. So the initial rating just based on the face, watched the video, made a bunch more ratings in the same traits. We narrowed it down to just these people. So we wanted sort of one example from each person because we didn't want to have sort of multiple trait updates at different points. Like that's complicated. And on these particular traits up here, using a process that was meant to find cases where people actually were updating, right? So not all the traits were actually updated equally by these videos. So we wanted to find cases where people were updating and were updating in generally the same ways as well. So we also are interested in individual differences, and I'm not really going to talk about that right now, but you can also choose videos that are polarizing, that some people sort of like think changes it in a really positive way and a really negative way. These are focused on consensus changes, right? So everybody sees this and thinks, oh, okay, I thought this person was like really shallow from their photo, but they actually is a lot deeper than I thought, or something like that, right? And then we used a tool that was developed in Luke's lab that we sort of repurposed for this, which was a continuous rating task, where they started with sort of an initial tailored starting point based on just a single judgment of the face and the first frame. And then they could update their traits over time as they're sort of seeing their using the sort of up and down keys on their keyboards to indicate whether they thought this person was like more nosy or less nosy in this case than the initial baseline that they started out with. And they do this over the course of the whole video. And that sort of time series of trait impressions was what we'd be analyzing here. So can we explain using nonverbal and verbal information, why these numbers go up or go down at any particular moment in time? Yeah, so this is the sort of data that then comes out of this process. This is just like sort of one example time series here. These look pretty different across people. And we've done, as I said, some individual difference work looking at like why, and it's related to a whole bunch of things that you might expect, like the personality of the rater and their attitudes towards members of different social groups and so forth. But again, focusing on sort of the nonverbals here, we actually sort of diffed this along the time series, so we could just focus on those time points where the impressions were going up or going down, right? So what moments sort of led to an increase in whatever trait you were rating or a decrease in whatever trait you were rating. And based on sort of this then diffed time series, we could generate a representational dissimilarity matrix to say at what time points was a similar thing happening, was sort of the trait sort of similarly increasing or similarly decreasing at different moments in time. And can we then predict that from whatever the features of the video were around that point in time? So just to focus on like one example of some of the nonverbals that we looked at in a little bit more detail, like here are the three rotational dimensions of head pose that you can get out of PyFeet, for example. So this is roll, pitch, and yaw. So pitch is like this, roll is like this, and yaw is like this, right? And between these sort of explain all the ways you could sort of turn your head around, right? And so these vary over the course of any one of these videos. And so you can see those sort of three evolving over time here. And we just take, 2 time points here now, not diffing this, but just looking at the raw values. And we can compare those 2 time points to generate a representational similarity or dissimilarity, if you want to talk about that matrix for time point by time point here. So for every moment in time, we can say how similar are these in terms of how people's heads were positioned at that moment in the video. And we can do this for any of the different types of features that we've annotated here, right? So this is kind of what we're trying to do in sort of metaphorical way, and not too far off literal, is take a trait-based representational similarity matrix and decompose it into some weighted sum of all of the nonverbal ones that we have. So we have, again, things that you can get out of pi feet. So things like the facial emotion score on sort of the basic emotions. Not that we are taking those too seriously here, but that was one of the things we could use here. The action units, the head pose. For voice, we looked at things like the frequency, amplitude, and spectral profile and temporal profile, and then we looked at the verbal content as well, meaning the semantics of the text that they were speaking during the time. So this was a time point by time point representational similarity analysis. And one important thing we did here was to include sort of multiple lags of each of the independent variables here. So it wasn't just like at that one single frame were you updating in the right way at the right time, because that's, I think we thought, pretty unlikely, right? That like it takes you like a beat to figure out like, how do I feel about that? How does it change my impression of a person? So we wanted to sort of be able to decompose that response, which might be temporally extended over time, especially because the continuous rater itself only affords sort of a certain amount of change over time, right? You have to like keep, pressing or hitting the button to create a larger change over time. This is a little bit like, you can think of it as a little bit sort of analogous to sort of like a finite impulse response model in just like fMRI data analysis. Yeah.
Yeah, I was actually going to ask about that point that you just raised, which is that like with the exact inputs method you use, you have to keep tapping down, right? And then people get bored and tired of doing that, I imagine.
Yeah.
Why not? I would be with, I use sliders for everything. So I just think, oh, sliders, let's throw it on a thing. But how come you didn't use something like a slider where you just like click lower down on the slider, right? If I make a big jump where I thought this person was a 70 out of 100, and now it's like, oh, actually they're a 30, but I could just go boom, and you see this huge drop.
Yeah, so I think there are a few issues. One is that, and this isn't necessarily solved by the way we did it either, but people kind of forget to like change things sometimes. So that's one issue, is like you get engrossed in listening to the story and you're like, oh shit, you have to change the rating. So we wanted to be like continuously valued. We didn't want it to be like you have to like remember to like hit a slider at every so often to change your opinions. And then the other thing we're going to try and do ultimately for this, when we take this into the scanner, is to not have people make these ratings at all while they're watching the videos, because it's super distracting, right? So we'll have some M-Turkers be distracted. And then we'll have our participants in the scanner just watch these totally passively, just like, enjoy the narrative sort of thing. And then using hopefully some of Luke's collaborative filtering stuff, we'll be able to create sort of customized multidimensional trade updating timelines for the participants in the scanner based on the M-Turk participants. So we can sort of sidestep a little bit some of the distraction that comes from that.
It's maybe silly, but then having like an actual tactile thing they can use for this may be best, right? Like if you have a dial. Right,
yeah, no, I agree. I think it's a question of like how we get that into the hands of online people in a consistent way, because people are using all sorts of different devices and stuff like that. So far these people have all been interpreters. Should have mentioned that. So yeah, but
tease out the distractibility. Like, do you have anything? It's like, what if you have like a task where it's like, or maybe you've done something like this and press a button every couple seconds, but then you look at parts of the film where like people's timing gets more variable or noisy or something, like that's measured distractibility, or how you just assume people are going to be distracted and that's like noise, or how do you think about it?
Yeah, so I mean, like, I think the one way that we've sort of most directly tackled this so far is just by comparing like the data that come out of the continuous rater from the data that come out of making just a pre-post rating, right? So like presumably those things should be related in terms of like where you end up at the end of the continuous rating, and they seem to be. So yeah, there's probably some distraction things going on there. A little bit unclear how to like get around that sometimes, but I'm hoping that the sort of like way that I mentioned might help us in the future. So we compute this sort of RSA, mixed RSA model, just multiple regression basically, but with all of these different RDMs thrown into it. And then what we do is we basically compute the AIC of the model that has either everything in it, or it's taken out one family of regressors. And by family of regressors, I might mean like, say, all of the different lags of the voice spectral regressors, right? Because there are like multiple of them, so I can't look at the individual parameter values for like just one of them. I want to get an overall quantification of like how much this like temporal feature matters. Yeah.
This is a very specific question.
Yeah.
But, I'm familiar with voice spectral features, but what are voice temporal
features?
Yeah, they're basically things like how much the spectral pattern is changing over like some window, basically. Yeah. Okay, so so this is all happening within an individual participant, and within an individual video, in fact, for that participant. So one model for one video by one person. Then we get an AIC change for each of these things, and we put that into a second level model, which is itself a mixed effects model that has random effects for the participant and the video in question. And that's where we calculate significance for all these things, and just slap a Bonferroni correction on it for right now to make sure that we're not being too optimistic. Right, so here's what comes out of that process. The different modalities are color coded here, and they're labeled along the bottom axis. And then the change in AIC, lower AICs are better, but I just reverse coded it because I think that's like a little bit unnatural to read. So like bigger numbers here, I mean, it's contributing more to the overall model fits. So you can see that actually all of these are statistically significant, controlling for multiple comparisons. So all of these things seem to be making some contribution to predicting people's trait updates over the course of watching these videos. But there's some pretty big differences between how much sort of the different modalities are contributing. So we're seeing, the acoustic features here accounting for sort of the most information, the facial information and sort of second most. And interestingly, sort of the text thing that we often think about as sort of the most important thing is actually, contributing considerably less than some of the other pieces of information here. But I want to sort of emphasize some important caveats on this and reasons why I think this is more just evidence that like nonverbals matter rather than like nonverbals are like relatively this important sort of thing. One is that this kind of assumes that all of these annotations are of equal quality. And that's probably not true, right? So it's a little bit difficult to compare sort of how good an annotation is across like totally different modalities. But my suspicion is that like there's no reason to believe that these are all equally good. We know that they're all not perfect, and so even on their like training data, never mind sort of transferring to this. There are also issues with sort of just, the distribution shift in the sense that, like, for example, most of the face models are trained on people who are not talking. These are people who are mostly talking. And therefore, that could go either way as far as the performance of the face model. It could be that like this is destroying the performance of the face models, or it could be that the face models are somehow picking up on verbal information and kind of stealing a bit of information by kind of like lip reading accidentally from the videos. So we don't really know either way what's happening as far as that's concerned. Yeah.
I missed it, but were there is this averaged across all different trait ratings, and were there differences in how modalities contributed to different types of trait ratings?
Yeah. So this is pooling across everything right now. This is just sort of the overall summary of it. We only looked at 3 traits, so I'm a little bit hesitant to say like there's like major differences between those. But most likely I think they're going to be ultimately. Where we really want to see some more information on that is when we have traits that are more polarized, and I think we'll be a little bit more diagnostic. Because right now everybody's sort of changing in the same way, and so it's a little bit hard to say whether that's just a function of like how we pick these particular traits, or it's actual substantive differences in how much the modalities matter to them.
Maybe what those 3 traits were.
Yeah, so it's I believe it's bossy. Let's see, we've done this a few times with slightly different sets. So this is aggressive, humble, and shallow. We've used a few more, like we're doing a previous replication of this right now, and so I think we've just switched to 3 slightly different traits. So we want to generalize beyond these particular ones, right? So yeah, as I was saying, I think this is sort of like proof in principle that like, these nonverbal pieces of information matter, and at least maybe some indication they could matter quite a bit. Could matter like at least as much, if not more, than like what specifically people are saying during these interactions. So not only interactions, but naturalistic narratives. So I think this is some nice sort of suggestive work of how we can move forward, trying to understand more naturalistic types of interactions and how sort of traditionally studied processes like trait impression updating play out when we're working with stuff that looks more like everyday life. So now I'm going to move on to talking about body language and conversation. As I mentioned, this is work building on the data set that Emma collected, in which participants had conversations with each other, sort of sitting across a table like you see here. I blurred out the faces not for anonymity reasons. I think you've already seen the unblurred part of this earlier, but rather because I want you to sort of focus on their bodies and look at the poses of these two people. And even without their faces or without hearing anything that they're saying or how they're saying it, I think you can tell something about the nature of this interaction. And I think if you look across lots of different interactions with different people, a lot of information is conveyed in how they position their bodies and how those positions change over time. And that was sort of a major focus of what we're looking at here. I'm going to focus on sort of two slightly different topics with respect to these data. One of them is sort of the eternal question of synchrony that's come up a few different times. And I'm going to sort of show or use this as a sort of an example case of how what you mean by synchrony can really change the answer to whether people are synchronized or not, or how they're synchronized and what time scale. And then I'm also going to talk about work trying to get a little bit closer to using deep neural networks, not just as sort of annotation tools for naturalistic data, but rather as cognitive models, and how we can start to make a more sort of permeable boundary between naturalistic and non-naturalistic types of study designs. Just to remind you, this data consists of a bunch of round robins of dyadic conversations. So half these round robins are women, half are men, and nearly all of the pairwise conversations happen between them. There are a few missing edges in those graphs to look carefully. And we just annotated all of these conversations using PAIR, which is a it's part attention regressor model. It's a deep neural network that was trained to do this task. And you can see in our video here, like what this looks like and sort of the ways in which it's good, but also kind of slightly imperfect. And again, that's what I kind of want to emphasize, that these things are like, they're getting there, but they're not like maybe 100% of the way there yet. So you can see things like there's some high spatial frequency, kind of like jitter or noise in these things. That's actually relatively easy to solve just by adding some like smoothing. There's some nice different smoothing models which have been developed to like try and deal with this particular sort of thing. It gets worse when you have things like people occluding themselves. So when the legs are crossed here, it can sometimes act a bit like a bistable image where it like switches the left and right legs real quick, and that's very unrealistic. And so this is one of the reasons why we're interested in the future, when we collect our own data, collecting sort of multiple viewpoints, so we can disambiguate some of those things, which are a little bit tricky for the models to do from one viewpoint. So we do this for all of the videos in this data set. And then the first question I was going to mention is, just how do people synchronize during these interactions? And this is going to depend a lot on, what you mean by synchrony, right? So is it the total amount of motion that people are putting out there? This is, all of these things are things that people have used as definitions. I'm not just sort of making these up as examples. These are out there in published papers. Is it sort of joint specific, like my right hand tied to your right hand in some way? Is it direction specific? Like, am I moving forward when you're moving forward, or am I moving forward and you're moving back? And what might be the time lags involved in these processes? Are we talking things that are happening over the course of like milliseconds, few seconds, tens of seconds, etc.? And then it also depends a lot on the structure of the interactions that I was mentioning earlier. And this is, I think, the case that's kind of been missing from this literature, which is like these really unconstrained verbal conversations, but also in person where people can see each other's bodies rather than, over Zoom or bodies obscured. So I'm going to focus first on this case of like total motion, right? So this is just like, how much are all of my joints moving? The sum of all of my joints moving in one particular moment. How much does that predict how much the sum of your joints is going to move in that moment, or any sort of moment in the next few seconds or minutes? And what we see here is, I think, kind of the opposite of what people have often argued as far as like body synchrony. People often sort of emphasize like people sync up. Actually, yeah, they really do not. They really are doing the exact opposite if you think about synchrony at this level in these unconstrained conversations, right? So there's some like slightly positive values, like at around sort of the 0 time lag there, where more movement in my body is correlated with more movement in yours, but those aren't even significant. And then there's this massive sort of inhibitory sort of effect where the more I'm moving at time 0, the less you're moving at times that range from, a few seconds out to up to about, 20 seconds out. So this is a very sort of long-term inhibition. These are only 10-minute long conversations. So 20 seconds is a long period of time. This is also much longer than the time scale of turn taking on average, right? The average turns in these were less than 3 seconds. And so, this is a multi-turn sort of state change that's being introduced by like me doing some weird movement. And you're like, okay, I'm just going to stop, right? And we don't have a psychological explanation for this yet, or even sort of mechanistic explanation for this yet. Yeah.
I don't know if I'm reading or interpreting right, but like with the same total motion characterization, like you could imagine some like a different kind of description of this is like how much is my total body motion related in any way to yours. So it's not only like are we doing the same thing, but like are they totally independent or are they related? So any deviation from 0, like you might interpret it as like, yeah, what I'm doing is connected to what you're doing. So
Yeah.
the blue could be considered as synchronization.
Right. So that's where I feel like we need to just establish sort of a more consistent and specific vocabulary rather than just saying like synchrony for all the things. I would say like, yeah, this is great evidence of like coupling, right? That these two things are not independent, they're shared information. But synchrony, I feel like probably should have like a slightly more like specific meaning where it's like, it's the same thing that's happening in some sense of same, though I think it's debatable what exactly that sense should mean. Yeah.
Is there like a law of conservation of total motion?
Yeah, that's interesting. We haven't tested that exactly, but yeah, that's that maybe is consistent with this. Yeah.
What you're saying is that they're meaningfully anti-correlated?
Yeah, so like, the more I'm moving right now, the less you're going to be moving in 10 seconds. Yeah.
Is that related to what they're talking?
Well, as I said, the turn length here is about 3 seconds on average. So this is actually evolving much slower than that. I'm sorry.
The intake peak is around 3 to 5 seconds.
It's more like 5 seconds out, 5 or 6 seconds out. So it's more like at least 2 turns, and it lasts. There's a negative deflection here that lasts like 20 seconds at least. So that seems substantially longer than like many turns, I'd say.
It's related to the length of the conversation. People will speak one by one, so this time
Yeah, so maybe let's put a pin in this sort of vein of questioning, because I'll show you a little bit in a second that there's actually something else happening that is much more sort of related to turn taking than this. And another point I just want to make is that this actually happens even if you look at things in a joint by joint way. So this is the exact same data, but now it's looking at the motion of each joint and each pair of joints being correlated. So basically, no matter which joint I'm moving, so I could be moving my wrist or I could be moving my ankle, whatever joint I'm moving is going to be predictive of all of your joints moving less in that sort of window of time. So yeah, there seems to be this sort of very generalized sort of inhibition where the more any part of me is moving, the less any part of you is going to be moving in the near future. Yeah.
Wait, can we do a sanity check on this though? Like, can they see every joint?
Yeah, they can't, right? But that is not necessarily problematic because the different joints that I'm moving are correlated, right? So like if I'm moving part of my body, other parts are more like, so yeah. Yeah, so this is not like the partial like contribution of each of the joints. Yeah. So this is like a sort of relatively long time scale thing, and it's not direction specific, right? So there's no information about which direction I'm moving. This is just like how much I'm moving. And the story really changes when you start to include that directional information, which is another piece that I think is really missing when we talk about like, is direction a part of synchrony or not, right? So now we're looking at again at paired joints. So this is now only looking at correlation between one of my joints and the same exact joint on your body. And it's now direction specific. So the sort of top, first row and first column are sort of the forward back dimension. So if, I'm facing Jeremy, it's like if I lean forward, does he lean forward or does he lean back? Right. Yeah. The second row and column are higher or lower. So if I sit up straighter, do you also sit up straighter? And then the last dimension here is like our lateral left right dimension, right? So like if I move my right hand, do you use your right hand or your left hand? And we're only looking at again, the sort of the paired joints here. So like, again, if I move my right hand forward, does Jeremy move his right hand forward sort of thing? And you can see pretty different patterns here. So in the forward back dimension, there's sort of an initial, very quick negative deflection. What this means basically is that if I lean forward, you lean back, right? But then this is quickly restored back to the original equilibrium, and this all happened in sort of less than 3 seconds. So this is much more sort of on the time scale individual turn taking, rather than the much longer time scale we were looking at previously. So this is where sort of the peak in the previous graphs would be, is like more like 5 seconds. By that point, all this directional stuff is pretty much done, right? Yeah.
The row and the column labels are the same, or?
Yeah, exactly. Sorry, yeah. So like this is this sort of like diagonal set of plots is like within the same. So like, for example, if you see a different pattern here between like sort of the forward back dimensions versus the high lower, like with the high lower, if you sit up straighter, I also sit up straighter, like more or less immediately sort of thing. Yeah. Yeah, exactly. So these are statistically significant, not controlling for the time points, because that's kind of an arbitrary decision about how many I decided to include here, but including corrections for all the joint pairs that are being tested at any time. Yeah. Yeah, so we see these things between like these coupled joints, but this is unlike the previous case. This is not universal across all joint pairs, right? So if I now introduce data from all possible pairings of joints, so this is like if I move my right hand forward, you move your left shoulder backwards, not just sort of one to one. You can see that there's some joints which are following the pattern that I was showing earlier, where there's sort of negative deflections, for example, in this dimension, and then positive ones later. But there are other joints which are positively coupled, right? So it seems like this could be reflecting rotational rather than translational symmetry, right? Or vice versa. So, for example, if I high five you, you usually high five with the same hand, right? Or sorry, that's a little bit ambiguous here. If I high five with my right hand, you're going to high five with your left hand. Similarly for like handshaking, right? Well, sorry, the opposite for handshaking, right? If I shake with my, sorry about that. If I shake with my right hand, you're also going to shake with your right hand. So some things are rotationally symmetric and some things are translationally symmetric. And this is actually really like difficult to parse in these sorts of contexts, because it's not clear what synchrony means. Is it the positive correlation or is it the negative correlation? Because either of those could be a form of synchrony, and we really need to think about like, is this rotational or translational symmetry that we're talking about when we're looking at synchrony, right? So this is sort of more of a problem than an answer that I'm posing to you here. We haven't worked out how to like fully make sense of all these data yet. Why are we seeing the patterns that we are? I think one possible answer is sort of proxemic station keeping. So just like sort of planes flying in formation, we probably have some sort of distance that we're like comfortable staying at with somebody. That could be different from different pairs, and it could evolve over a period of time. But within any conversation, probably like I don't want to be that much closer or farther away from you. And so again, if you close the distance, I might reopen the gap and so forth. Yeah.
Do you do sort of like physical model? It's like, if you're going in for a handshake, you have to come closer, and like your hands have to be coordinated.
Right.
But if you're doing some sort of like full body, like communication sort of thing, you might need to step back to see the whole thing.
Right. So yeah, again, thinking about what actually tends to happen in these conversations, people don't actually have to do many physical actions. And I'd say qualitatively, I can tell you there's like, there are handshakes at the very beginning of the conversations, but that's pretty much the only time that people touch each other. And then, and that actually also sexually dimorphic, where like, men tend to do that a lot more than women actually. And then there are a few goal-directed actions, like sometimes they like reach for something on the table. There are a few sort of like ambiguously goal-directed, like I think they're sort of goal-directed, but maybe like a little bit unconscious sorts of actions. Like there's a lot of like chair repositioning, like shimmies and this sort of thing. And then the most common type of movement that we see is just like people doing this, right? They're moving their hands as they talk, sort of thing, right? So yeah, I think, one thing we really want to do in the future is collect a broader range of actions, because I think we're seeing like a pretty narrow range of like types of actions, and it might actually shed a lot more light on these types of actions to have in relief some which are a little bit more goal directed or a little bit more sort of like coordinated between people. Another thing that people, sorry, go ahead. Yeah.
have you seen or read anything about maybe some like cultural differences or something when it comes to these kind of like emotions?
Yeah, so I mean, there is a pretty rich literature on proxemics in particular that like there are differences and preferences for how close people stand to each other in different countries. So if you're at the same bus stop as like a Finnish person, that's too close, whereas if you're like nose to nose with an Argentinian, then like that's perfectly comfortable. Is a sort of idea. But we don't really have the right sample here to look at a lot of that. The undergrads are somewhat diverse, but like we just don't have enough sample sizes within different communities to make any strong conclusions about that. Yeah, so I mean, people do often sit at fixed distances from each other for pretty extended periods of time. I think like meals are a great example of how that usually happens. But we want to figure that out in a bit better detail. So like one thing which I think my lab and maybe Talia's lab are going to team up on is using sort of our full audio visual recording rigs to have bigger groups in this space actually come in and interact in sort of like a more like cocktail mixer sort of setting where people are making decisions about like when to disengage with people and when to re-engage and how close to stand and this sort of thing. We'll be better positioned to answer those questions with those data.
I'm wondering if one possible way to look at synchrony that might get at things a little more closely and how they play out during conversations would be to look at states, like stable states rather than motion. Because just thinking about the kind of synchrony I typically experience in conversations, it's like, yeah, it's like one person's waving their hands a lot while they're talking, and maybe I'm just sort of nodding, and that's pretty asynchronous. But then there's like these longer things like crossing arms or like legs being crossed in a specific direction, like those tend to mirror each other.
Yeah, so I don't have the data in this slide deck, but we have looked at that. So basically, one thing you can do is kind of like a person pose RSA type of approach, where you take like the RDM of all of my joints in physical space and all of yours, and just correlate those sort of distance matrices with each other. And contrary to, I think, what a lot of people might expect, including me, but particularly in the existing literature, those sorts of like static positional similarities are like completely uncorrelated with like connection ratings, for example. So we have continuous connection data for all of this. And most of these data, regardless of whether it's static or dynamic or total joints or individual directional things, none of it really seems very closely associated with connection, feelings of connection. So I don't know how much of that is like the fact that people are like reflecting on connection after the fact or other issues there, but so far we have not seen really any type of connection between connection and these things. But I think the static poses in this case are it's a very clear sort of like cluster solution if you want to do it that way, where it's basically there's like arms up like in front of you, one arm up, the other arm up, both arms down. And those are sort of like the four poses that people make at a course level. Those people definitely do them. Whether they're like doing anything psychological for like, sort of high level stuff like connections seems unclear. One thing these body movements might be doing though, especially the fast time scale ones, is signaling turn taking. So these are just like averages. These are just kind of like get an fMRI if you like have like trial wise averages, so you can see time courses. This is very much like that for sort of total motion, relevant to either the onset or the offset of a conversational turn. So the red line, vertical line, is indicating when in the left-hand panel. It's left, right. The left-hand panel, like when somebody starts talking, when somebody stops talking on the right. And you can see that there are really big deflections in these things, but they're not exactly the same either, right? So the temporal profile looks a bit different, where right before you start talking, you actually like move a lot less, and then you sort of suddenly greatly increase your movement, and then it sort of trails off over time. And these averages, to be clear, so this could span multiple turns here, but we've only included data where this reflects one turn, right? Because we don't want it to be like just the fact that like, oh, well, I could stop talking here and I'm averaging in data where I'm not talking anymore. No, this is you talking continuously on a long term. That's why it gets a little bit noisier out to the ends as well. So that's another thing that these movements could be doing, that we haven't come up with sort of a mechanistic model to sort of link these profiles with the synchrony data that I was showing you earlier quite yet. Largely because I've been the one playing with these data mostly, and it turns out I have less time for that now. The other thing we've been doing with these data is, again, trying to use sort of a more cognitive modeling approach, where we train a model to like look at gestures in this case, and compare what's inside of that model, the representations inside of the hidden units, with what is potentially within participants. And we haven't actually gotten this part of it yet, but we're sort of taking some steps in that direction. I just wanted to quickly illustrate what that could look like. So we're using this model called Barlow twins, which is a type of self-supervised model. These are great because you don't have to like tell the model anything manually. You have to go annotate the data. But they can still learn representations, which are both one, like super useful. Like if you do a self-supervised DeepNet, it can learn a basis set for classifying images in ImageNet that's like pretty much just as good as a fully supervised model. You just need to give it a tiny bit of like training data at the end. These models have also been shown in domains like vision to really closely approximate what's happening in a lot of those domains in the brain. So we don't know yet for social stuff, but I think it's a reasonable thing to try and do. The general sort of pattern for these self-supervised models is you take in like one piece of training data, you augment it in different ways, so you get like two copies that are somehow different from each other in ways that you want the model to learn are not important, and to learn that these things are actually still the same. In this case, we're introducing into the body movements, we're introducing for temporal noise, where like sort of things are happening in sort of like a jagged temporal way, and also spatial noise, where maybe like the joints are slightly differently positioned than they actually were in the original video. And in this case, this uses sort of this interesting loss function, which is basically trying to learn as many sort of independently decodable dimensions as possible. It's one way to think about that. So when you do that, and then you throw it into a UMAP to get sort of a low dimensional representation, this is sort of what that looks like. So each one of these points is like one gesture that lasts, probably, generally they last like about a second on average. So there's a pretty wide range for those things. So we have, tens of thousands of these across the course of all the videos that we collected, and you can throw a clustering onto this. This is a density-based clustering approach to get a bunch of different clusters to describe that. And then you can start looking at things, and I think maybe Eleanor, this is getting back to some of your question earlier, which is you can look at things like transition probabilities between totally different gestures. So no longer like, are we synchronized in any particular way, but more generally sort of, are we coupled in some way where like, if I do one thing, you do something else, which doesn't have to be the same thing, just later in time. So this is sort of like what some of those data look like. I'm not really going to talk about the patterns in this point. But what we would like to do in the future is to sort of test this model against the brain, right? To see, okay, we've had this model learn some representation of gestures. Is that representation of gestures similar to what our brains learn spontaneously as we're trying to parse out other people's body movements? And one of the problems with this is we really don't want to show the original video data to participants in the scanner because there's so many confounding variables there, right? There's the identity of people, there's, all the stuff they're doing with their faces, and there's information that the model doesn't have access to, like finger position, because these models are not annotating that actually. And so we just wanted to have the people to have access to the exact same information in a non-confounded way. So we want a nice controlled traditional fMRI experiment, but we wanted to somehow come directly from this naturalistic data. And one way we can do this is by sort of generating like average versions or sort of stereotyped versions of particular gestures from each of those clusters. So what we can do, for example, in this case is we took 64 examples from a given cluster and we kind of paired them off. And then we spatially aligned them using the Procrustes transformation. So this is a rigid body transformation where I'm just sort of rotating you into the same frame. And we apply dynamic time warping to align the gestures in time. So like if if we're both waving, but I started waving slightly earlier, we can like warp those things in time to be better aligned. And then we just average these things sort of pairwise until we take 64 to 32 to 16 to 8, et cetera, just get one final gesture. So here's some actual examples of gestures that were part of the same cluster as recognized by our algorithm. You can see they all involve people having both hands behind their head at some point within this. And then this is a point light display that we generated based on that. And you can see again that people start with their hands behind their head and they bring them slightly down during the course of this particular gesture. Here's another couple of examples. This one is a lowering arm gesture. So here is it from one perspective, and here are totally separate data that were averaged to create the same sort of representation, and the person's facing the other person here, but they're both sort of lowering their hands. And then here is the same gesture from sort of the side and the front. So again, sort of lowering hand and lowering hand from the front.
What are people like?
Oh, sorry.
Is this, are these?
So sorry, I should take a step back. These are what are often called point light displays. So these are,
Yeah, sorry.
yeah. So each one of these dots represents like one joint as defined by our body pose model. So these are nice like low level controls because like you can't see anything about the person except for like the relative positions of them, and you can do things like I could scramble the motion of the joints relative to the identity of the joints to create something that has like the same motion, but like is unrecognizable as like a human moving. And yeah, these
It's like point in 3D space.
yeah, each joint is a pot. Yeah, exactly. So these have been often used to study like biological motion in past research. Yeah. So the basic idea here, frankly, I think we still have work to do on these. But the basic idea is to take this sort of situation we have sort of these two walled off worlds of like naturalistic data and controlled data and make this sort of a bidirectionally permeable sort of membrane between them, right? So when we need control, we can have it with data that comes from the natural world. And then ideally, we can also go in the other direction as well to take sort of controlled cases and generate what, sort of fleshed out version would look like. I think, Stefan's example earlier is a good case of that. And the final very brief part of my talk, because we have no data here, so I can be really quick, is trying to do causal manipulations on interactions. So we recently got funded to do sort of our first project in this vein, and this is a really neat illustration. All the illustrations in this talk are from Lindsay Tepfer, my graduate student, who's becoming a really cool science illustrator in addition to a scientist. So this is basically trying to figure out like, can we shape the direction of conversations using conversational content as the manipulation? And it's also a cool art project. So the idea is this is funded through our arts integration initiative at the Hopkins Center. And the basic idea is that you and another person will come into the art museum. And one of the things you could do there is come to this table and look at some art on a screen in front of you with some headphones and a mic on. Having a conversation about the art with each other. And just like you may have experienced in actual art exhibits, you sometimes overhear other people in the exhibit talking about the same thing that you're looking at. And this is basically meant to sort of recreate that sort of experience. So what will happen is that your speech will be automatically annotated using first a speech to text model and then a language embedding. And then those language embeddings, those numbers that represent the meaning of what you're saying, will be kind of like a search term for previous comments that other people in this experiment have made. So somebody else earlier on might have said, wow, like I don't like the guy on the left, he looks really sketchy or something like that about some piece of art. And then if you say something that's potentially related to that, like, oh, the guy on the left looks kind of untrustworthy, I don't know. Then the next moment there's a gap in your conversation with your partner, that comment from a previous participant will be played back over your audio. That's the idea. And what we can do with this is if you think about the conversation as sort of moving through this sort of high dimensional semantic space, naturally, so this is you and your partner sort of taking turns saying things, then we can locate these sort of possible intervention comments as being close to what you just said. And then we can randomize which one we choose so we can have some idea of the causal impact of playing that versus the other possible statements. And we can see how this sort of changes what you say next, right? Does it pull you closer to, the comment that the other person made that was just inserted? Does it deflect you away from it in reactance? Or how does that sort of dynamic play out as a way to figure out how we can actually shape discourses in a causal way? And I think the other direction we can take this as sort of the technology continues to develop, this is maybe not quite where it needs to be yet, but it's getting very close, is basically using deepfakes.
Here's the very funny Bill Hader, ladies and gentlemen.
So this is an example that I often use in my classes of deepfaking
like every
in real
movie
time,
I saw
well,
last
not real
summer,
time
you
processing,
were in
but like real time.
And good for you. That's thanks, buddy. Thanks. And
So you'll see
I was
Bill
wondering about
Hader's
the one,
face
the
some
Tropic
interesting things
Thunder.
here.
Yeah,
as he does
Tropic
some
Thunder.
references.
Tom Cruise. You're working with Tom Cruise. What was that experience like?
It was amazing. Like we got to dance together. That was amazing. We had like when you do a movie, you do table reads, where like all the actors get together.
At the beginning of the
beginning, before anything, you get together and you read through the script. And so it's like, all these heavyweights, like, Ben Stiller, Jack Black, Robert Downey Jr., everybody. And then at the end is like me, like, like, hey. to be here, guys. And some other supporting guys. And then Tom Cruise walks in. And even those guys are like, whoa, and he's super stoked to be there. You know, just like, yeah. You know, like he's immediately excited when he walks into a room. And so he comes over and he sits next to me. And I think he had been briefed on some of the supporting guys, but he was like trying to place me, you know? So he sat down next to me. He's like, I love your work. Oh, thanks. I love your work too, Tom Cruise.
Okay, you get the idea now. So this is the kind of thing which, rather than manipulating identity, as you see in this particular case, I think we'll soon be able to do with respect to other nonverbal information, right? That we can manipulate things like people's facial expressions or tone of voice or prosody in real time in relatively seamless ways that allow us to intervene in interactions via the medium of the interaction rather than by some sort of outside force, right? So I could be talking to you during a conversation and I tell a joke and you actually laugh, but instead I just got a neutral face looking back at me. And how does that affect how I feel about our interaction, right? It's sort of idea here. You could even imagine doing things like completely synthesizing parts of the conversation, right? You know, you feed in what I just said to ChatGPT, it comes up with some response, and I used a fine-tuned text-to-speech model that's tuned on your specific voice to synthesize your response. I'm literally sort of putting words in your mouth. And again, this isn't necessarily something which is like quite ready yet, but given the pace of things recently, I think we're looking at this being a reality within the next 5 years for sure. So I think another possibility that you can do with this is to make these interventions contingent on behavior. So just as Tali was talking about earlier, with sort of the gaze meeting thing being, you know, contingent on what was actually happening in the conversation, we don't just want to like insert these things at random moments in the conversation, but to really probe in a nuanced way. Like, if I do this, when you do that, how does it affect what happens next, right? And this, I think, is sort of the basis of what's going to give us the ability to, you know, have a causal science of interactions in the near future. Okay, so that's actually the total sum of my talk. If you want to read more about sort of our ideas on all of this stuff, we have a review paper that's just accepted at Effective Science, and another one that's a preprint from me and Bo Stevers, where we talk about how we think sort of deep learning can enhance the future of studying social and emotional processes. And I'm happy to take any questions.
I have a question for your first part. So you're showing the, you know, the model space of the factors or aspects of conversation that matter. I mean, are you doing work trying to map the specific features of each one of those elements onto trait space?
Yeah, so one of the things we've been trying to do is actually use deep nets as, like, you know, sort of the cognitive models in that context too. We've been running into some issues there where like individual people's data is like very noisy. So you kind of want to average, but then when you average the data, you lose a lot of the individual differences, which are actually carrying a lot of the variance, the perceiver's individual differences, that is. And so I think we either would need like a lot more data or to figure out some way of otherwise sort of circumventing that sort of problem, because so far those models have not performed very well. So we don't really have sort of good answers to like what the specific feature mapping is. And we kind of expect it to be nonlinear in a bunch of different ways, right? So I think this is like taking a linear model of one thing to the other is not great, which is why we use the RSA approach instead.
And then for your gesture studies, I mean, I guess this is also a question about just designing fMRI experiments that are looking at naturalistic conversation. I mean, would you expect that observing gestures is similar to the process of generating them in this case?
Yeah, it's an interesting question. So I mean, there's like, you know, all the sort of mirror neuron work, which suggests that people are like interpreting these gestures using some overlapping regions, the ones they use to produce them. I have mixed feelings about some of that work, but you know, I think probably there could be some, you know, overlap. We obviously don't really want people making the gestures in the scanner. I think we may get some more traction on this when we have the interactions that actually have people in the scanner as part of them, right? So what we're trying to do in the lab now is like take studies that we're going to run, like just with people face to face, like you saw with Emma's data, and sort of, I refer to it as like half hyper scanning, but that doesn't really make any sense. But it's basically like having an interaction to split across a person outside the scanner where they can move freely, we can observe them, and the participant inside the scanner can also observe them. And the participant in the scanner is like maybe not moving, or at least maybe only doing like facial expressions or something like that, which doesn't interfere with like the head motion side of things. And that can give us maybe a little bit better traction on whether when there's an actual interaction going on, somebody's brain in the scanner is, you know, decoding the gestures and doing things in response in the same way as when participants are just passively viewing gestures. Yeah.
The transition probability or matrix that you showed was really
Yeah.
interesting. I mean, would you expect that if I were to observe you making, you know, gestures that I wouldn't expect to be followed after each other, that would kind of generate surprise?
Yeah. I mean, you could look for prediction error signals for sort of unexpected gesture transitions, whether that's like repetition suppression or some other sort of pattern. But yeah, I think that's definitely one of the things that we could do with that. Sure. Yeah. Sorry, I wasn't sure who was first. Yeah, I mean, I guess I keep having the sense that like I'm doing something wrong, but I cannot find really any strong connections between correlation, sort of between feelings of connection and anything people are doing with their bodies during these conversations so far. We've tried this in like very generic ways, like ways that should capture like any sort of contingency there, and we really don't see anything. So maybe it's something about like some of the ways we're doing it on the body pose side, or some of the ways that like the connection ratings were collected, but so far we have not seen much happen.
It's like a type of crowd control method that people use, which is like you force like an echo, right? So if you're talking, if you're saying something and then you hear that same thing that you just said played back at you, like with a 1 second delay or something, you just shut up.
Yeah.
Is there a similar sort of thing for non-verbal behavior? Like as in like if verbally, yeah, verbally. But non-verbally doesn't work, right? So for example, if you use these deepfake methods to have, you know, you look like say I'm looking at you over Zoom.
Yeah.
But your body motions are actually just mine. Played back a second later.
Yeah.
Do I just like freeze up?
I don't know. I think it'd be super fun to run that experiment. Yeah. Yeah, that'd be a great experiment to run. Absolutely.
It's like, it's a different things you can data. I've been like, this burning. Because like, yeah. It feels like the conversation thing, there are very stereotyped, like nonverbals that are specific to the speaker role and the listener role, where I'm not nodding that often while I'm speaking. But you know, I nod a lot while I'm listening, or I kind of like make like or like, you know, these kind of like family things. Whereas like, yeah, I probably like gesture a lot more while I'm speaking and like don't gesture as much while I'm listening.
Yeah.
And I wonder like, just it feels like a lot of the structure in the body motion is going to be determined by like the current like role of conversation. And I wonder whether just like segmenting by those roles and then looking like within the listener role, are we adapting like how much we nod or something? So it's not going to be time locked. It's going to be like you take onset of the listener turn, and then you like pair them up there. So it's like when I start being a listener and you start being a listener, and like you might expect some kind of like, I don't know, like increasing adaptation within the listener role or within the speaker role.
Yeah, no, I think that's definitely a good possibility. Generally, yeah, your intuition is absolutely correct that people move their bodies pretty differently when they're speaking versus when they're listening. Though I would also say that there are pretty big individual differences just qualitatively in that. So I'd say there are certain gestures where if you're making them, you're almost certainly speaking. But the absence of them is not necessarily diagnostic of you not speaking. There are a lot of in these particular videos. There are a lot of these videos of like these like I don't know, they look like athletes. They're often wearing like Dartmouth gear, and they're just like sitting back in their chairs like this and like not moving at all. So yeah, the absence of movement is not necessarily the absence of speech, but yeah, I agree with you that like maybe trying to think about this as like two different spaces, and like one being contingent on the other is a good path forward there. Yeah.
Like, I'm more thinking like actually certain gestures when you're are you something else. You're now talking while you're talking it goes this, which can be reasonable. Some degree, well, I'm not what you were talking. I'm telling you.
Yeah.
So it's like it's a you need to explain that behind it.
Yeah. So like the meaning of these things is contingent on like what role you're occupying. Yeah. And maybe one more. Yeah.
Yeah, I don't know if there's any research to actually support this, but I wonder if mirroring body positions is less about connection per se and more about something like simulating the other person's mind. So kind of going back to the title of your talk of like interacting minds and interacting bodies, maybe it's like in some way, if your body simulates the other person's body, it might help give you a window, your mind a window into their mind.
Yeah, no, I think that's definitely a possibility we should look into. Yeah, and that bears on all levels of like connection with the other person, because sometimes you're not feeling connected emotionally with the person, but you still want to understand their mind, right? Yeah, I don't know if we have quite the right dependent variables in this data set, but those are definitely things that we're going to be getting in the data sets we're starting to collect right now. Things about like, how aligned you are in representing the mind of a third person, for example, or how quickly you pick up on like changes in the state of the group based on their referrals. Yeah.
Just follow up on a couple of comments there about the connection. So one, I think it's really variable, and most likely when people are making those judgments, they're probably focusing on the content of what people are talking, but that doesn't mean in general it might be this path. But another thing might be that because they're so subtle, they might be the deviations from their baseline of how they adapt to that person. That would be this really small signal, but that would be like the chameleon or like stuff. And because it has the pairwise stuff, you might be able to parse out how much that person is changing with that specific individual or their normal baseline. That might clean up and remove some of the variation.
Yeah.
It's just one.
No, that's a good thought. Thanks. Yeah. Okay.
Mark.